So welcome back, everyone. Hopefully this week and next week we'll be able to present the new proof, which gives an exponential improvement on multicolor Ramsey numbers. So that will be really our focus over the next 2 weeks, this week and next week. Let's just remind ourselves what we know already for this multicolor case. So, well, I guess the part we're doing now is new upper bound on multicolor Ramsey numbers. As we've said, there are many beautiful results you can do looking at other problems, not just the one with cliques, but we're going to focus on the one with cliques because that's what the new results about. So I'm just putting on some air conditioning here. I should also mention, actually just a small thing, but on one of the slides, I think something said about K-form multiplicity was wrong last time. Anyway, so if you're interested in K-form multiplicity, it's a very interesting problem, and you can go and read about that and see what's really true. Okay, so let's start with what we know already about multicolor Ramsey numbers. And the first thing is that the Edler-Sekresh algorithm, exactly the same one, which gives you the upper bound of like, so Edler-Sekresh for two colors, you have RKL as opposed to K plus L, choose K. Exactly the same argument, the inductive argument, where you just choose a vertex, you choose the largest neighborhood, looking over all the colors, in which color does the vertex take largest degree. The same argument, I'll just say implies, well, it's really the same argument. The argument implies that if you have K1 up to KR, in the R color version, so this is, I guess maybe, should I define it? Okay, I'll just put the result. So, okay, I'll put the definition here as well. So this means you're going to use R colors, and R, the Ramsey number of this list is the minimum n, such that in every R coloring, in other words, using 1 up to R as the names of the colors of the edges of Kn, there exists a monochromatic K, so complete on Ki vertices in color I for some I. So either you want to precise K1 color 1, or K2 in color 2 up to KR color R. Okay, so it's a natural generalization of the upper diagonal Ramsey numbers. And the upper bound of Edler-Sekresh is that you sum on top, just in the same way as we have two colors, and it's the multinomial. So it's the multinomial where you're choosing K1 up to KR. In other words, it's the same number, this is the same number as the number of ways to color just K, well, this many vertices with R colors, and you're going to use this color K1 times and the R color KR times. In the same way as choosing a subset is the same as coloring with two colors and fixing the number of times using each one. Anyway, this multinomial in particular, if you just do familiar bounds, Stirling or something, is at most R to the RK. Actually, when we come on to doing our upper bounds, we're really going to think of the bound a lot of the time anyway. We're going to think of it just being this one. Sorry, I've done this wrong. I'm supposed to just remember R to the RK when I get to the diagonal case. So we'll get to the diagonal case. Diagonal case would be, we use this notation for the R color diagonal Ramsey number. We already mentioned it actually. And so this is at most, like, this bound is most RK But then you say choose k, the multinomial coefficient, and this one is most r to the rk. In fact, this r to the rk has the same role as 4 to the k does for the usual two-color case, because it's slightly bigger than the corresponding coefficient, but the difference here is only a polynomial k. So if you think of fixed r and large k, this difference is just a polynomial in k. So we can sort of ignore the difference between these two things. So for example, when I write down the theorem saying get an exponential improvement, we can just get an exponential improvement compared to this. So it's worth maybe we could mention as well, if you just want to do the end of separation bound and get that upper bound, the r to the rk, you can do a slightly simpler argument. I mean, the argument's already very simple, but you can do a slightly simpler argument. In the same way as for 4 to the k, you can just go, you could just ask, do I have more neighbours in red or blue? Suppose you start with, let's do 3 colours. Suppose you start with at least 27 to the k, I guess maybe 3 to the 3k vertices, then you can do a very simple argument to show you can always find a monochromatic clique. You just take any vertex, and at least a third of his neighbours will be joined all in the same colour. And then you take any vertex in there, at least a third of his neighbours joined in the same colour, and so on. And so after you've done this, let's say you do, after a certain time, you've done B blue steps, R red steps, and G green steps. And the number of vertices left would be at least 3 to the minus, was it, B plus R plus G times N. Well, remember what N is. N is 3 to the 3k. So 3 to the 3k minus B plus R plus G. And what this says is you will still have vertices left until one of these 3 gets as large as k. If all of these are less than k, then you still have vertices, you can still run the algorithm. And of course, if one of these does get to be as large as k, if you look at all the vertices joined in blue, for example, that will actually be a clique size 10. So this is the sort of slightly even more direct, even easier argument you can do if you just want to get that. And all these things I'm mentioning because there's going to, it's going to kind of be relevant that we have this idea going down by a factor of r every time is the sort of natural order of magnitude for things to be going down in the Ramsey argument. And so there'll be times when we say, even today, look, if you manage to do a similar argument, but you're going into neighbourhoods of size a little bit bigger than 1 over r, you're already doing well. You're already maybe winning enough to win the factor 1. Okay, so I was talking just quickly through these ideas, because hopefully some of them are familiar, but it's good to just know we're definitely agreeing on the context. I thought I'd just mention, this is just a small thing, but numerically speaking, it's sort of funny. The bounds do feel like they get worse as you go to more colours, in the sense that for 2 colour, you've got root 2 to the k is at most, maybe we'll get rid of that bit of the argument. Root 2 to the k is at most the Ramsey number for 2 colours. And the upper bound is now down to 3.8, right? But for 3 colours even, the lower bound is basically, what is it, 1.84, I think. If you work it out from the lower bounds we mentioned in the other lectures. And as I said, the upper bound is like 27. Okay, so numerically speaking, you can just see the gap is growing already. And it just carries on, in a sense, getting worse. So Of course, I'm going to say it's a really great thing to be improving this 27 by a tiny, tiny bit. But of course, there is still a huge gap, and you know, it'd be interesting to know in future if we can get real progress in shrinking. Good. So let's mention the new result. So new result. So first, we'll spend a little while listing the authors because there's 8 people. But I'll be slightly efficient and say it's CGMS. So therefore, on the first paper, and we'll just say there's 4 new people joined us for this paper. So we've got Ballister, Bolabash, Hurley, and Tiba. Paul Ballister, Bailey Bolabash, Owen, Hurley, and Marius Tiba. This is a union of 2 sets. So the new result is we can get an exponential improvement on the multicolor Ramsey numbers as well. And so the following form, if you fix any R, I'll say at least 2 because it still works for ours 2 as well. You can find some positive epsilon, which may depend on R, and such that then the Ramsey number, our color diagonal Ramsey number, is at most e to the minus epsilon k times, well, as I said, you can just put the R to the RK as the existing upper bound. Technically, you should say we should be improving relative to this bound, but as I said, it's just a simple check. The difference between these 2 is just a polynomial factor, so an exponential increase doesn't really care about polynomial factors. So that's our new result. One, I mean, you could say it's a slightly disappointing thing is as R gets bigger, we sort of know this upper bound is growing, you know, and getting even further and further to the lower bound. You might hope that our epsilon is growing as a function of R. It's not growing as a function of R. I think it's like maybe a multiple of R to the minus 12. It goes slowly to 0 with R. Because it's not so slowly, it can still work even when R is large or even going to infinity to give you some improvement on this upper bound. But as we said, it'd be really nice to actually get even epsilon a fixed constant bigger than 0, independent of R, or even better, somehow growing. No. So anyway, let's get on to our perspective from the point of view of this course. What are we going to do here in the course? And I think it might be more natural for us to put as our theorem 1. Maybe I'll even put it on top of this. I'll put it on top of it. I'm going to put just the 3 color case. Okay. So it's a special case. And the idea of just doing a special case is if you do general R, then every time I put in some constant, really it should be a constant which is some function of R. I think it all gets a bit more complicated in terms of keeping track of how these things relate to each other. Now I'm going to make a different choice, and I'm not sure everyone will think it's the perfect choice, but I'm going to do a presentation where I use more actual constants, right? So I'm going to put in, as we'll see, even in the first statement, that the 3 color Ramsey number diagonal Ramsey number R3K is the most e to the minus K, and I'll put in an actual constant. It's over 2 to the 110, okay, times 27 to the K. So we'll use 4 actual constants, and this has advantages and disadvantages. And the advantage is you can always tell how it relates to the other constants, right? You know which one's bigger than which other one. I know it seems a bit less elegant in some sense, but I think that's, for a course, I think it makes more sense to present like this, and then hopefully we can. I think in many ways the presentation given in the article is a slightly more elegant one than maybe we'll do here, but I think hopefully we can go through the details better this way, hopefully. So what's the plan for today? And as you can say, to stay in the rest of the course. So we'll start by discussing the relation of the new proof to the old proof. Remember, in the last lecture we gave a quick overview of the old proof. In other words, the proof that gave the first exponential improvement, the 2-color case. Well, and its subsequent developments and adaptations. And I think that'll just be a way to discuss the new proof informally and get a feel for, similarities and differences. Well, yeah, as part of that, we'll then give a sketch of some of the ideas of the new proof. We'll then do something which is a bit more formal, and we'll reduce our problem from this to proving something we'll call the book theorem, which is, well, we'll see in a minute in talk more formally our books, but it's saying that a certain structure can always be found in any colouring. And then we'll try and give an introduction of an algorithm that will be central to our argument. Probably for today, the statement I'll give the algorithm will still be a little bit informal, because the formal statement depends on a geometric lemma, which we'll do in the next class. So the next class will be much more geometric. We'll have this funny geometric fact, which looks like it has nothing to do with colorings at all, but turns out to be exactly what we need. And then there'll still be some remaining details, quite a lot of remaining details really, to check that things work, which will come next week. So let's remember what a book is, because I'm saying it's going to be central to our argument as well. So so we have some coloring of Kn and a pair of disjoint sets let's say AB is called I could call it AB. I mean, we're going to use T and M for the size of the books for some reason. TM book in color I if, well, I guess T and M just refer to the cardinals of the set. So A has size T, B has size M. I could have done A and B at this point, right? And what structure do we want? We want that if you restrict the coloring to A, you see a clique in color I. So, in other words, to be a book, you want A to be such that all the edges in A form a clique. I guess it would be in color I. This is color I. And you want that all the edges between A and B are complete color I. This is what we. Okay, so to be a book, you need a clique. So a red book, for example, will be a red clique. All the pairs in A are the same color, red. And between A and B, you want all the edges to be of the same color. And why is this important for Ramsey proofs, even as we used in the old proof, and it's been used, well, in many other even in previous decades, and discussed a lot with respect to Ramsey bounds. It's easy to show if there exists some Tm, well, let's say some monochromatic Tm book for some positive T, with T at least 1, and the other side of the book being at least, so n at least, the Ramsey number for, let's think of 3 colours then, K, K, K minus T, then you're done. Then the colouring, well then there exists a monochromatic clique KK. So it's easy because the remaining part of the book is large enough. You either find in one of the first 2 colours a clique of size K immediately, and you're done. The third colour here represents the colour of the book. So if in any of the other 2 colours you find a clique of size K, you're just done. And if not, you find a clique of size K minus T in the remaining colour, the colour of the book. And together with the T verses on the other side, they form a clique of size K. So this basic fact is sort of implicitly, well, sort of essential to both the previous, well, lots of upper bounds in the past, including the previous exponential improvements to 2-colour, and to our new approach. So as I said, we can, I don't know if this is the best way of doing it, but I thought it's somehow, it's one way to discuss the new proof and some aspects of it, to mention the similarities and the differences, because I think some people have already seen that proof from last year and maybe want to think about the new proof in relation to it. So I think there could be some use to doing that. So similarities to old proof. So I guess both rely on finding monochromatic books. And, well, there are probably lots of other similar things in the proofs. I'll just put some technical aspects. I mean, there are lots of places in the details of proofs where you realise you're doing something somewhat similar. So for those of you who remember in the other proof, we have to make some decision of how much density are we willing to lose in a step and make up some alpha. And we're going to do a very similar alpha here. And maybe there's some other points in analysis that are quite similar as well. It's not so surprising that you get something similar. So maybe more interesting, what are the differences? So now I can do it sort of as an arrow going from the past to the future, whatever. So previously, the approach was very asymmetric. In the sense that we said, we have 2 colours, red and blue, let's find a red. Now, that was a fairly arbitrary choice. In some sense, it was, well, it's definitely, at least you can say it's breaking the symmetry in an important way. Whereas the new approach is completely symmetric with respect to the colours. We're basically going to try and build a book in each different colour at the same time. And so the argument, the algorithm is completely symmetric with respect to the different colours. Another difference, this is slightly more technical perhaps, but it's how big is the book that you find. Well, big is the strange where you've got 2 parameters. So you can be trying to build a book where T is very large, and you don't need much on the other side, so you're most of the way there. Or you could be doing a book where T is very small, and you just got a few steps. And that's another difference. So the first argument, you really need, it's absolutely essential that you do large T, you do a large number of steps. And in the new approach, we're going to have very few steps, in a sense. Now, each of these comes with different advantages and disadvantages. One of the advantages of when you're just doing a small number of steps is that you don't need to be nearly as efficient on what we think of as the left-hand side. There'll be a set X in a minute when we present the sketch of possible vertices to join the sort of left-hand side of the books, the cliques in the books, and you don't need to be nearly as efficient about controlling the size of X. You can lose much larger factor every time because you're only going to do a few steps. So it's just a technical thing, but it does make a difference in how you are trading things off and what you care about. Another difference is the previous proof talks a lot about density. You need to know about the density of the red edges between the two sides. And we're now going to change that to a min degree condition. It's a similar idea. They're both about demanding a certain number of edges between the two sides, but just with slightly different conditions. And one you're really interested in, this is basically equivalent to an average degree condition across, whereas we're going to switch to a min degree condition. And there's one important technical reason why this is in some ways better, and it's the following. If you have a minimum degree from one set to another, so I guess it's going to be X to like Y or one of the Y sets anyway. This makes more sense in a minute. If you have a minimum degree condition from here to here, in other words, every vertex in X is a certain degree across, then you have an extra degree of freedom in a way, because you have the fact that if you pass to a subset of X, you'll still maintain that property. You don't have to think twice about it. If everyone in X has a certain degree to here, and I pass to a subset, then that remains true. Whereas if you have a density or an average degree property, you need to worry, you know, what happens? And, you know, there's other ways around that. You know, you can try and remove versus low degree before, there's other things you can do. But it's quite convenient actually to work with a min degree condition for this reason. So maybe, I don't know if I'm overdoing this comparison, but I'll maybe just say one more thing about the comparison, and then we can do a little bit more in terms of the sketch. So you could also think about the comparison in terms of advantages of the old proof and the new proof. And, well, as we saw, even from our first statement here, the new proof is not terribly good at giving you strong improvements in the bounds, right? We've got a pretty small number we're getting. So, so maybe the old proof is better for getting better bounds. In particular, if you take the new proof and apply it to two colours, which you can do, it just gives you, well, the version that's written down gives you like 2 to the minus 160. Anyway, you probably can't do better than a 2 to the minus 20 or something. It's not optimized. So the old proof could definitely give better bounds. The other thing about the old proof that was quite nice was this asymmetry is actually very natural if you're in an off-diagonal test. So for off-diagonal Ramsey numbers, the old proof worked particularly well. Then being asymmetric wasn't really it wasn't such a weird thing to consider, because you really had a difference in the densities already. The asymmetry was given to you. Anyway, one of the advantages of the new proof, I guess the main one we're trying to sell, and giving a talk about multicolor Ramsey numbers, is it generalizes to multicolors, or works in the multicolor case. Okay. The other one I'll mention is, I don't know if this seems a bit vague to you, but in some ways it's conceptually more pleasing. Well, as an opinion, I have, or we have, and you can see after, if you watch a bit of this course, see if you think there are. I think there are nice ideas there. So I'll try and communicate that. I'll try and get that across, and we can hopefully convince some people that there's some truth there. Right. So let's get into more directly speaking about what the proof looks like. And in some sense, I think it might not be much of a surprise, given, well, as we said, the last proof we saw, given the ways we said we're going to go about changing it. So what would the argument be? Well, we could, let's say sketch. So let's just say the first objective is to try to find a monochromatic TM book for the version we're going to try and do here in class. I can just let you into a secret. We're going to try to do T is K over 2 to the 30. Okay. So the number of steps the number of vertices you want to have in that clique in one of these colors, color I, will be a very small, or relatively small multiple of K. And obviously, M is at least the Ramsey number K and Ms. As we said, unlike the previous argument, we're not going to decide at the start, oh, I want to do it in red, I want to do it in blue, I want to do it in green. We're going to build in all 3 colors at the same time and just see which one works. In that sense, it's similar, I guess, to the original Ed or Shekresh, or the argument we did here, where we're just building in the 3 colors and just seeing what happens. I will say there is a reduction first, which even we'll do today. You can reduce the case where all of the degrees are roughly equal in all of the colors. So we can reduce the case where every vertex has degree about 1/3 in all of the 3 colors. So we'll do the details of that today. So we can reduce the case that all degrees, I guess I should say all color degrees, like all degrees, are approximately 1/3. Well, and you can actually also decide to partition right at the start into a set X, will be used as sort of the candidate vertices to form the cliques that are in the books. And we'll have on the other side, in the previous slide we had a Y, here we'll have Y1, Y2, Y3, and these will be the vertices that will be on the other side of the books. So if you do this, I'll leave the draw X bigger over here. Then let's think what a red step would be. So maybe you look at some vertex in X. It has a good red neighborhood, perhaps, in X and in Y1. So what do? Maybe you say, I'd be very happy to use this vertex in the red clique. So you'll move this vertex into, let's call it T1. And then you need to restrict X to the red neighborhood of this guy in X. So you restrict it there. And you need to restrict Y1 to the red neighborhood of this guy in Y1. So in doing so, this will be a red step. And in doing so over time, if you repeat this, what you make are you'll build three cliques, T1, T2, and T3. X will be such that it will only join in red to the red clique, and it will only join in blue to the blue clique, and it will only join in green to the green clique. You can see X may well shrink quite quickly. There's quite a lot of things it has to do. Whereas, of course, the other side here, they only care about being good to one of the cliques because that's all you need for a book. So Y1 will just be joined in red to T1. Y2 will just be joining blue to T2. And Y3 will just join in green to T2. So in a sense, I'm describing what is still the naive version of the argument. Because if I just allow you to do the steps based on who has the biggest degree inside X, so I take a vertex and I use that to the side, there are still things that can go wrong. But it's the basic idea of the mechanism we're going to follow. So what can go wrong, I suppose, is we're also keeping some sort of track of a minimum degree condition between X and Y1 in red, just given by some P1, between X and Y2 in blue, which is given by some P2, and between X and Y3 in green, which is given by some P3. By P1, I sort of mean that would be the condition that, like, for all X in X, the neighborhood in color 1 of X in Y1 is at least P1 Y1. That's what that would mean as a minimum degree. So we have this basic setup. Now, I guess we'll wait till a bit later to work out the other detail we need to add. But what's the thing that can still go wrong is if you do a red set, you may lower the minimum degree between here and the neighborhood of this guy up here. That's sort of a genuine problem, possible problem, because if you were just restricting in X, as we said, it's kind of cool. The minimum degree can't go down. But if you're restricting on both sides at the same time, that could be a problem. So how should you think about that? Well, you can think for this vertex X, you can sort of encode his neighborhood in Y1 by a vector. A vector, I mean, you could do it with a 0, 1 vector, like the indicate function of the set. Maybe it's even better to rebalance it, so the average value is 0. But anyway, you can kind of encode his neighborhoods here as some vertex Vx. And maybe for everyone in X, you can encode their neighborhoods of Y1 so you've got a sequence of vectors that encode neighborhoods in Y1. Really, I mean, neighborhoods in color 1 in Y1. You're only really ever interested in the red edges there, or the blue edges there, or the green edges there. Now, what happens if you have a pair X and Y? What does it have to happen for X and Y to be sort of a bad choice that lower the degree for the future? They're bad, so that X, Y is in some way bad if the minimum degree condition for Y to this neighborhood is worse than you had before. Right? So what does that actually mean? It means the neighborhoods in color 1 of Y the new set would be the neighbors in color 1 of X in Y1. And it's bad if this is less than, the previous condition had like a P1, and maybe you're willing to lose a little bit, which is some little alpha. But if you're less than P1 minus alpha of the new neighborhood, this would be somehow a bad pair for that step. And what happens is if you do the definition of these vectors correctly, which isn't even too difficult, this is actually equivalent to a certain negative inner product of Vx and Vy. I mean, I can put minus alpha here, or you can renormalize differently, and it's like -1. So what you'd like somehow is to find a vertex with good red to green, and such that this bad event doesn't happen with too many of his neighbors. However, there's a big problem. It could be that for all the pairs that he's good with in red, they're coloured blue. And with all the pairs he's good with in blue, they're coloured green. And all the pairs he's good with in green, they're coloured red. And so that's our nightmare, right? So there's a perfectly plausible nightmare situation where for every x in the left, he has a good neighbourhood across, or the neighbourhood across property is okay for many pairs, but in all the pairs where he's good in red, then they're coloured blue. All the colours where he's good in blue, all the vertices where he's good in blue, they're coloured in red, etc. So then you get the ambitious idea, which may seem too good to be true, but it's the ambitious idea at least, which is at least some epsilon portion of the pairs. I guess I could just say x squared, right? Because it's epsilon times x squared. Pairs. I mean, I didn't really say what's good. Good is in this language, I suppose, would be inner product at least minus alpha. We're going to do the normalization differently, and the good will be big at least -1. But anyway, what would be really ambitious to say, I can find a certain proportion, it's an epsilon, it's like a sum. I can find these epsilon x squared pairs here, which are good simultaneously for all of the books across, all of the colours across the respective whites. Good in all colours across. So that's our ambitious idea. And that would kind of require, it's really like 3 different ways of associating a bunch of points in Rn, or Rd, or whatever it is, with, so each vertex, gets mapped into Rd 3 different ways. And then you want to find lots of pairs that get mapped to good inner products, not to negative, in all 3. And I think maybe I'll have a dramatic pause and say, we can do that. And the geometric lemma we'll see next time is the secret to that. Okay, so I'll leave that as a bit of suspense hanging in the air. And we can, or perhaps, suppose, maybe just take time for it. You can't always do this. If you can do it, then you can find a way to do one of the 3 steps and not lose too much. Anyhow, if you can't do it, then instead, this geometric lemma will give us a different property, which is that the sum set of points which are kind of bunching up in one of these ways you code them as vectors. And that gives you a way to get a density boost. So maybe, we'll come back to more details when we do obviously the geometric level next time, we'll have a proper statement, we'll get all the right details in place. But if we do get a dichotomy, this works, well, unless it doesn't. So this works unless you have what you could sort of say, we used to call this a cap-like behavior, which just means well, if you thought of it on a sphere, if you have a cap and you have many more points than you'd expect in a cap. So we're not exactly going to phrase it like that, but either you are able to find this small proportion of points that are good for all the books across, and therefore, well, those pairs have to be coloured in some colour. So whichever colour dominates amongst the good pairs, then you could use that. Or somehow you find a fair number of pairs. Now, it could be quite a bit less, but we have to be careful quantitatively about our statements. And we find a fair number of pairs where they're in products of each other surprisingly big. And that corresponds to, if I go into this guy's neighborhood, the other ones get a big boost in their degree. And so that offers you an alternative step. So again, there's an alternative type of step. Our main objective is to build books in all of the colours simultaneously. But if this ambitious idea doesn't work out and you have some problem, then instead you do a boost. Right, so now let's say something a little bit more concrete. And what we're going to start with is reducing theorem 1 to a statement which is just about finding a book in a certain multicolored setting. We can do this in 2 steps. We'll first have like theorem 2, and then we'll have the book theorem, and basically we'll show theorem 2 implies theorem 1, and the book theorem implies theorem 2. So theorem 2, well, theorem 1, okay. Theorem 1, Ramsey. What does this mean? It means if I have this many vertices, and I 3-color that complete graph, I can find a monochromatic cake. Good. 2 is going to say almost the same thing, except it's going to ask the colouring be near regular. So, and actually it's going to have slightly fewer vertices because we need this difference to be on our side. So, as I said, we're going to use actual numbers, so delta will be 2 to the minus 40 for us. And theorem 2 says if the edges of maybe we should put the n as well. Okay, just work out your order to state this. That n be e to the minus k over, I think now 2 to the 67. Sorry, times 27 to the k, and well, let the edges of Kn be 3-colored, but we put an extra condition with all color degrees. I'll put cold decks, color degrees. In other words, for every vertex, for every color, the degree in that color is at least a third 1 minus delta. Then there exists a monochromatic cake. If the books are obviously good at different colors, And the book theorem is just going to say, instead of finding a KK, I can find a book. Maybe I'll just change the statement a tiny bit more again. So, well, delta is still 2 to the minus 40. Let n, now I think you just change it by 1, so 2 to the minus k of 2 to the 66 times 27 to the k. And the idea is, so, no, so it's not n. We want each of our sets. So let x, y, 1, y, 2, y, 3 each be at least e to minus k of 2 to 66. Makes sense to k. These are disjoint sets. Let's just say be disjoint sets. And such that, well, now we want the degree condition, but we only need the degree condition actually from x to each of those. Such that for every x in x, and for every I is 1, 2, 3, the number of neighbors in color I of vertex x in yi is always at least a third minus delta times the size of that set. Okay, so it's like the picture we had over here in our sketch. We wanted to start with x, y1, y2, y3, and at the start, of course, we want to have reasonable red density to y1, and blue density to y2, and green density to y3. That's all we're asking. You want the sets not to be too small, and you want that for all guys in x, they have a reasonable density, at least a third minus delta, to the corresponding sets in the corresponding country. So, yeah, the statement we're making now is that actually it suffices to prove the book theorem, because the book theorem implies theorem 2, and theorem 2 implies theorem 1. Actually, this first implies here, we won't say very much at all, because it's kind of, I didn't even finish the statement of the book theorem, so I should probably say a bit more about the book theorem. Then there exists a monochromatic TM book with, I think, well, it doesn't really matter. I would say, well, some T at least 1, and then at least Ramsey, K minus. So I won't say too much about book theorem implies theorem 2, because you quickly see the argument. But what do you do? Well, if you're in the state theorem 2, then you have a 3 coloring of n vertices for this value of n, and the degrees in each color are at least a third 1 minus delta, or in other words, it's a third minus 1 over 3 delta, in fact, in each color. Well, then I just do a random partition of the vertex set into x, y1, y2, and y3 by Chernoff with high probability. Each of the sets is at least a quarter. Sorry, at least an eighth, let's say. A quarter would be the expected value. With high probability, each is at least an eighth. And you can check, this is k big, the difference given away here is actually much more than a factor of 8. So I should say that the theorems are all trivial unless k is like 2 to the 115 or something. Good. Or anyway, the theorems. So by Chernoff, you can assume all the sets are large enough for the condition here, and degrees as well, right? If you take some vertex in x, what's its degree in y1 in color 1? It's just binomial its original degree So it was at least a third minus 1/3 delta times n, and the probability that a given neighbor is put into y1 is a quarter, right? But you're going to compare this to the size of y1. So y1 is in fact very close to concentrate around its mean. Anyway, right, I mean, I don't want to go through the details of writing out Chernoff proofs, right? By Chernoff, you can reduce to having sets of the right size and up to giving up with delta, 1/3 delta, 1/3 delta. You can ensure the correct degrees. I suppose there's maybe something with these statements where I kind of think you can go up to a fairly large value of k trivially. Maybe I should just put for all k sufficiently large in these statements as well, and then there's less worries that maybe I haven't got the probability bounds of k is small. Anyway, these already only really care about k sufficiently large. So it's quite an easy thing. It's only really an exercise. Should a book theorem implies theorem 2. So let's see that theorem 2 implies theorem 1.
So
yes.
Just one, I think it's a silly thing, but I just don't understand how y1/3 minus 1/3 delta, because delta is small, right?
I'm saying, what was the minimum degree condition that you already have in this statement? Because here, it's just a small difference, almost tricky. But here, only 1 minus delta in brackets. So the minimum degree condition you have in theorem 2 was, I probably should have like an n here, shouldn't I? It's really n over 3. It's probably an n. There's one thing. Anyway, because this is 1 minus delta in brackets, right? It's saying you try to introduce n over 3 minus delta n over 3. And in the next statement, I put the delta outside, third minus delta.
Oh,
so there's actually a gap. So I'm throwing something away, and it gives you enough room that Chernoff can say that's unlikely, right? Okay, so why would theorem 2 by theorem 1? Actually, if I'm just saying like the sketch reason or the reason you should believe this, it's also very direct. Because here we go. We have to think, okay, so theorem 1, we want to prove we're given a 3 coloring of e to the kn at n is e to the minus k of 210 times 27 to the k. Now, we'd be very happy if this coloring was super regular, because we could just apply theorem 2. Right? I mean, this is bigger than this, right? Your exponential term will be very much smaller. So if you happen to the start to observe, all the colors are used the same number of times every vertex, you're very regular, then you're just done by theorem 2, you can find them monochromatically. What's your problem? Why am I doing problem in sort of quotes like that? The problem is actually something which is usually good news. It's usually good news in a Ramsey argument if the degrees are varying. Because if the degrees are varying, then there's someone with degree quite a bit bigger than a third. And so you can do an Edler-Shekaresh step, but instead of going down by a third, you go down by some factor that's a little bit more than a third. So at least a third. I guess you could say it'd be 1 plus delta over 2, maybe. Right? Because there's 3 colors. If one of the colors is less than that for some vertex, then one of the other colors is at least this. I guess it's say I want to see the third, it's like proportion. Well, and then two things can happen. Either in here, all the colours are magically very regular. Well, you've only lost a small factor and you can apply theorem 2 and you can still find a clean gradient. Or you can carry on. If you manage to carry on for a number of steps, which is at least some constant times k, then you've won a meaningful factor, order k times, and so you've won an exponential factor in k. So that's basically the argument, but maybe I can write a little more, because I said this is the bit we're doing more carefully. So you could say you're going to take a maximal, or really an algorithm then, we'll say it's an algorithm. Okay, so apply the algorithm. Apply an algorithm. You start with X just being the whole vertex set. And it's like building 3 cliques. I'll call them S instead of T, because that's going to confuse us with the other argument. So we'll start empty. And what do you do? If there exists a vertex in X, X in X, with the degree in some color I to the rest of X is at least a third plus delta over 2 times X, then add little x to Si, and you restrict the set X to this neighborhood, right? I'm just writing out in details the same thing we did in that picture, and indeed in any able separation proof, which is that after a certain number of steps, you have a set S1 that's just joined in its color to X. So I'm putting little S1 here, which is this could be the cardinality. I guess I should use 3 colors. S2 is just joined in red, and it has the size of S2. And S3 is just joined in green, has the size of S3. And if you think about the size of X, the point is each time the multiple you go down is at least a third, and you have a 1 plus delta over 2. And this would all be to say little s, which is the sum of the sizes. Okay. Now, if this goes for a long time, then you're just going to win. Okay. So how long does that have to be? Well, it's better. I'll just say it's case. I think perhaps the statement of the book theorem we're not necessarily going to need immediately afterwards. So maybe we'll go here. So let's state these 2 cases, just to do it carefully. So case 1 is this at some point holds. In other words, it's impossible to find that new vertex. And it holds while the number of steps you've done, S, is less than K over 2 to the 68. Sorry for the horrible numbers. But this is just a way to say it stopped soon. Well, our plan, if it stopped soon, was to use theorem 2. And I guess it's just a case of checking the numbers, right? So then all degrees in X, then for all X in X, and for all I, meaning 1, 2, 3, the degree of vertex I in so vertex X in color I in the set X is at least a third minus delta of X, because remember, if any vertex had less, then you could find it one of the other 2 colors plus delta over 2, you can do that step. So the other thing is, because you did so few steps, you really didn't use up, you didn't shrink the vertex set too much. This is actually a point where we're being very inefficient. If you're trying to be an efficient person, you'd say, well, I've already got some cliques out here. I don't need to find a whole KK in there. I could find less. But we're being very inefficient with this theorem 2 implies theorem 1. That's why the constant is so much worse. But, you know, it'd be a bit uglier to have to remember things. Anyway, we're just going to say we didn't go down by very much. The size of X is at least, well, you lost at most a factor of 3 every time, and you did it most that many times. And this is at least 2 to the minus k over 2 to the 67. And therefore, maybe yeah, anyway. I've given away much more there than the difference of this actually. Oh, sorry, this should be E, I guess. Well, anyway, it doesn't really matter. These things about, you know, constant value. You're going down, you haven't gone down very many steps, and so even afterwards, you have large enough size. And so what you do, you apply theorem 2 just in the rest. And of course, we already have the nice degrees in here because that's why we stopped. And given we have the nice degrees, you can apply theorem 2, find a monochromatic KK. So there exists monochromatic KK by theorem 2. Good. I knew I'd get annoyed at some point by having chosen 2 real questions. You know, otherwise you have all sorts of. Okay, so what's case 2? Case 2 is that you carry on for a long time. Well, then we're going to say we've already won an exponential factor. Okay. So case 2, okay. So if we're continuing for at least this many steps, then we can just choose to stop when S is equal to K over 2 to 68, right? But then what can you say about the remaining set X at that point? So you can say it's at least, well, you lose a factor of 3 for every step, except not quite a factor of 3, because you also had the 1 plus delta over 2 for each step, times your original n. And this is just now some calculations. This is at least e to the delta over 4. So you've got e to the delta s over 4. And n is e to the minus k over 2 to the 110 times 2 to the 70k. Or in other words, 3 to the 3k. And then what have we got? 3 to the 3k minus s. And the point is, this factor you've won is bigger than this guy, right? Because delta is like 2 to the minus 40. This is 2 to the minus 68. So it gives you 2 to the minus 108. It's a 4. Okay, they're exactly equal. So these two guys cancel. What you have is this, which is at least the Ramsey number of k down. K minus S1, K minus S2, K minus S3. Right, because this is upbounded by the multinomial, which in turn is upbounded by that. Which means we can find the monochromatic clique. Well, sort of by the usual argument, it's just like the 3-color version, where we've so far found, you know, S1 in red, S2 in blue, S3 in green, and the remaining set you get to find either K minus S1 in red, or K minus S2 in blue, or K minus S3 in green, which when you join together with the respective sets, will give you your monochromatic K. So I think that's enough for that description. So this implies monochromatic. As I said, it's perfectly legitimate to think of this proof as just being the very obvious kind of statement. If I win a constant factor order k times, I must have won an exponential factor overall. And okay, you just need to work out exactly what you got. As I said, we did it in a very inefficient way because you may have done quite a lot of steps, and then even so, you just decide to ignore the fact you've done those steps. So this is not an optimized thing. On the other hand, optimizing doesn't make very much. It's not so important because even so, the bounds are getting up. So strong, right? Right. We'll pause a second. Okay, so I think next time we'll get into the details of what we mean by this geometric lemma, exactly how that will be applied in our setting. But if you don't mind, I think I'll just say a little bit more and perhaps, prepare the context for, what that's going to be about, how it's going to relate to the algorithm. Because again, in all these approaches, it seems we at some point define an algorithm. And that was the case, in the last proof where there was a book algorithm, which says this is how you're going to go and try and find your book. In that case, a red book, because you fix the color. In our case, it's an algorithm that's going to be finding all these books at the same time, because we don't know which one is going to work. So we'll give a first informal definition of the algorithm today, just so we know what it's going to be. And in fact, it's actually much simpler in some sense. You could say in another sense it's kind of complicated because it relies on the geometric lemma to define it formally. But in another sense, it's simpler because it has less cases and less steps. So, in a sense, what the result for next time there's lots of black pens. Oh, this one. This one. So the result next time says, so this again is still a bit informal, but it says either you can do a reasonable color step, which means a color step in which you don't lose too much in terms of your minimum degree condition in one of the colors, or you boost density. So maybe even in saying what a reasonable step is, you lose at most alpha in the min degree condition. In a second, we'll have a short discussion of what is alpha as well, because that matters. Or we boost density by density, I really mean the min degree condition, min degree, by some large multiple of lambda times alpha, with lambda large. So this sounds like a great thing to be able to boost the density in one of the colors. What's the cost? The cost is felt mostly in the set X in this reservoir. And it costs something of the form, at least, e to the minus root lambda in the size of x. And it turns out that this trade-off is not at all clear a priori. Don't think you ought to be able to instantly understand why that makes it a good thing to do. The trade-off turns out to be good, and you only really need that this is, what do you call it, sub-exponential. It's just going to zero, but you don't want to, if you were losing exponential, your x would be going down too quickly and it wouldn't be well. But if you're losing something else sub-exponential, you're actually doing pretty well. There's some weird constants and stuff as well, but that's basically the statement that we'll have next time. And let's mention the alpha and mention, as I said, the informal statement of, if you like, we can call it the book algorithm. I mean, the book, we called one of the last paper the book algorithm. So we should probably call this like the multicolor book algorithm or the multi-book algorithm, or we had some debate about what's a good name. If anyone has a better name. But maybe I'll just call it the book algorithm because, you know, or maybe the books algorithm. There you go. The what?
Library.
Library algorithm, yes. What is many books? Many books is the library. Yes, that's a good one. That's a good one. The books or library algorithm. And so, I mean, yeah, this is going to be a bit too informal again. Basically, because there's a lemma here which I haven't stated, but it gives you one of two things. It either gives you a situation in which you can do a reasonable color step, and it's like we said in the sketch before, it either gives you epsilon proportion of the pairs are good for all the colors, and then you want to do a color step, or it somehow gives you this other situation. And it's what that lemma gives you that decides your action. So you somehow encode all these bipartite graphs of the colors you have to the other side by vectors in different copies of RD. You apply this geometric lemma to those points in RD, and the geometric lemma decides what type of step you should do, really. If you find a positive proportion that are good for any type of color step at the same time, then we'll be able to do like one of those color steps. Otherwise, we're going to have to do, well, we don't have to do, but the only reasonable thing I think we can do is the density boost. Okay, so if in some color you can do reasonable color step, then we do that color step. And then otherwise, I suppose I'm making it too simple if I just say otherwise do the density boost step. Maybe we could say, just to be a bit more serious, what it means in terms of the steps you start with. You start, you're even given, when you do the book theorem, you're given X and three sets called Y, right? And these are all big to begin with. And I guess we start with T1, T2, and T3 being empty, right? These are the things that are going to be the cliques in respective colors. So what do you do in the color set? You add some vertex V to the clique that's colored I. You restrict X to just be the neighborhood in color I of V. And you restrict YI to be the neighborhood in color I of V. yeah, one thing that's useful again with the minimum degree condition, here you're restricting x. If I take a yj, which is different from yi, then it's okay. The minimum degree condition between x and yj does not change, because going to a subset of x does not change the minimum degree condition. And the density loss in colour I goes to something. Maybe I should. Sometimes you need to. We were doing I to be an index of time in the other paper, but I guess we use S for time. So your previous time minus alpha, lose the most alpha in the colour you're doing the step. That's what is included in this reason. And else, you density boost. So you do a particular type of step which will increase the density in one of the colours, right? And yeah, I mean, it's a bit more difficult to say because you need to work out what's the correct subset, which comes from these pairs. But you restrict x to a subset, and you restrict one of the yi's to a neighborhood of some color in that yi. And again, when x goes to a subset, it doesn't change the minimum degree condition to all the yj's, but you will get an increase in the condition for this one color, plus lambda alpha for some large lambda. One thing we didn't say yet, well, I've kind of hinted at it twice, I think, we didn't actually say it in any more detail, is how much density or minimum degree are we willing to lose in a single step? Well, one thing is you don't want to lose very much, because even if you carry on for t steps, you don't want the density to go down very much. On the other hand, you don't want the enemy to just be able to give you boosts forever. And so it's very similar to, we mentioned this in the sketch of the other proof, you want alpha to actually be a function of the current density, and alpha to become larger if the current density has already gone up. Like betting more if you've already made profit. So we use, so in a sense, it's going to be different for each color, because it depends on the current density in each color. So that's the I. And it's different in each step, because as the condition changes over time, the amount you're willing to bet changes. So what do? You take your current density, you subtract, right. It's all going to be around a third, probably, right? Because you start off with densities around a third. In fact, you know you start at least a third minus delta. And you may as well decide that you want a third minus 2 delta to be the absolute floor, right? You never want to go for the third minus 2 delta. So what you do is you only bet a proportion of how far you are above third minus 2 delta. And we'll just divide it by t. T is, of course, the number of steps, the maximum number of steps you're going to try and do in any one color. So if you bet this much, if you lose every time, you still lose, you still stay above this value.
Só não entendi como que a gente escolhe a cor para dar um boost para o signo.
Right, so in the case, basically, yeah, I suppose you could say it was too soon to try and do this description of the algorithm, because in both cases, I didn't give the full description of the choice of the color. But let's give just an intuitive idea of what that choice is like. So in the first case, it tells you there's some tiny proportion, maybe, but some positive proportion of the pairs in X are in magic pairs that are good for all types of step. They're happy if you do a red step using them, because their red neighborhoods are nicely correlated, and their blue neighbors are nicely correlated, and their green neighbors down here are nicely correlated. So there's some magic pairs in X. It may only be 1 in a million, but there's some of them. Well, then what you do is you say, well, if it's 1 in a million, then there's some vertex that at least a millionth of his neighbors are super good. That's just double counting. And if you have some vertex and a millionth of its neighbors are super good, they work well for all the different colors, then, well, these edges have to be colored with some color. And you just look at what's the majority amongst those. And then at least 1 over 3 million or whatever of his neighbors are super good and in a certain color. And if that happens, then you can just do that color step. So that's the description of the choice of the color for the first type of step. If this doesn't exist, what the geometric blender will say is that in some color, in other words, some, well, think of these different RDs or sets of points, whatever it is, but anyway, really in one of the colors, you have this opportunity. And the lemma tells you, I found you this opportunity, it's in color 2, right? And therefore you follow that, you do the boost in exactly the color it gives you. But somehow the way this trade-off works, the way these things are, there's not really a good way for your opponent to use these boosts against you. If he keeps trying to boost, at some point all the densities get up to 1, and then there's no more they can do. And it somehow turns out that, at some point they're forced back to actually doing book steps, and then you manage to make your books. So I think that's all maybe we'll say for today. I know I sort of pushed a lot of the serious talk to next class, where I said, we'll do the geometric lemma, and we'll really see the details of that. And I guess, probably, hopefully, we'll also maybe state the algorithm again, but be able to say it with full rigor. Does anyone else have a question or anything? Okay, so we'll leave it here for now. Bye.